So this lesson is on compound interest, and there's a few things going on here, and I really want to spend more time helping you a little bit with the calculator and how to understand these formulas rather than just memorize them. So I'm going to leave the solutions on and just kind of talk through some things. So this first formula is just the compound interest paid n times a year. This is the compound interest formula if P dollars, so that's the principal that we're investing, deposited at a rate R, so that's the rate R there in decimal form. Compound interest paid n times per year, so n is the number of payments per year, or number of compoundings per year. Then the amount A, that's the amount of money will be in the account after t years, so that little t appears up there in the exponent. It's given by this formula, so that's P times this quantity, 1 plus R over N raised to the NT power. And so we'll use this formula multiple times. It says you should have it memorized. Alex gives it to you, so you'll end up with it memorized because you use it so many times, hopefully. One habit I always encourage students to do is write down the formula before you use it every time. So we're going to go through just a few examples here. If you have $5,000 in an account, pays 4% interest, how much we have in the account at 5 years, interest is compounded yearly. So that means if it's compounded yearly, that means n is 1. That's the number of compoundings per year. Notice the next problem, compounded semi-annually, that means n is 2. If it's compounded daily, we'll either assume that it's 360 or 365, and I mentioned this in another video. Many books will say assume 360. Alex says assume 365, and just follow the directions is really what I tell students. So if the problem says assume 360, then make your fractions out of 360. If the problem says assume 365, then assume 365. So in general, this first one, 5,000, 4%. If it's 5 years compounded yearly, then so the 5,000 goes here, 1 plus 0.04 over 1 raised to the 1 times 5. And so I know that may look a little bit funny right there, but there's a 1 right there in the denominator. N is 1 for this problem. So 1 times 5. So 1 times 5 is just 5. So 1.04 to the 5th is that calculation. This one is 0.04 over 2, and so that's 1.04 over 2 raised to the 2 times 5, and so writing it the way I wrote it right here is exactly what you type on a calculator. That's the caret symbol for exponents. So you could type 5,000 times parentheses 1 plus 0.04 divided by 2, close the parentheses, raise that to the, and then you have to put 2 times 5 in parentheses. Failure to put this in parentheses will cause lots and lots of mistakes. So the other way to avoid that mistake is to multiply 2 times 5 and just get 10. If you raise it to the 10th, then it won't cause a problem. So that's just something important to point out. Now if it's daily, notice it's the exact same problem, 5,000, 1 plus 0.04 over 360. Raised to the 360 times 5, so that's the way you'd type it on a calculator. And notice with each of these, starting back to question A, here you got $6,083, here you got $6,094, here you got $6,106. So it turns out the more times you compound the interest, the more money that you would make. So that's just worth noting. And they're all still approximately $6,100. They're not too far apart. Different question. How much money should be deposited today in the account that earns 6.3% interest compounded quarterly? So quarterly means n is 4. So that it will accumulate to $17,300 in 8 years. So that's $17,300. That's what you want it to end up at. So that's A. So there's $17,300. Note if we put all the stuff in here, and then we're trying to figure out what P is. So P is the thing we don't know. How much money do you have to put in now for it to grow to that number later? And so there is the way you would type it. So if you actually divided, looking at this line right here, if you actually divided both sides by this mess, I cleaned it up a little bit. 4 times 8 is 32. So if you divide both sides by this whole mess to get P by itself, so now this line here reads that P is 17,000 divided by all that ugly mess. 1 plus 0.063 over 4 raised to the 32nd power. And if you wanted to type that on a calculator, you would type 17,000 divided by, and then big old parentheses, so an extra parentheses and then the inside parentheses. And I'll show you what that looks like. So that would be this. Clear that off. So it looked like 17,000. 17 or 17.3. I feel like, yeah, 17.3. Didn't want to do the whole wrong problem. 17,300 divided by, and then first thing you do is hit parentheses twice, because the first one is the whole denominator, and then the second one is 1 plus, and then that was 0.063 over 4. So get up there. 0.063 divided by 4. That's now closed in parentheses. Raise that to the 32nd power. And then close parentheses. So now that's my whole denominator. And then when I hit enter there, I get $10,492.22. $10,492.22. So that's where that calculation came from. So just practice manipulating. So the point is, you're going to use this formula a lot. Sometimes you're going to have different number of compoundings, so that's going to change n. Notice n appears twice in the formula, once up in the exponent, once in the denominator. Sometimes you're going to not know a, sometimes you're going to not know p. If you don't know t, it gets really complicated. There's where we can use our calculator, and I'll say more about that a little bit later. Again, question 3 is similar to question 2. It's almost identical, so I'll let you just practice that one on your own. Solving for P. If we use this effective annual yield, so there's that y equals, and I feel like, got these at the end here. Yes. So I was going to say, I thought maybe that was one of the times that Alex used a different letter. These are all the Alex formulas here for you to use as a reference. But Alex doesn't use a different letter there. And I'll show you those calculator things here in just a minute. So let's see, there it is. So you've got an account that pays 5 1/4 compounded quarterly. So quarterly means n is 4. 5 1/4, that's 5.25%. So the effective annual yield is 5.35% because it's compounded quarterly. So question 5 asks you to actually compare two things. So suppose you've got a savings account interest rate 4.2% compounded daily. So that's assume the 360 days in a year. Suppose another is 4.3% on an account, and that's just simple interest, 4.3. So which one is going to be better? Well, if you do 4.2 compounded daily, you get the effective yield here. Turns out to be 4.289. So that's not quite 4.3. So actually the 4.3 simple interest is slightly better when you compare those two. Now we get into this annuity formula. That annuity formula is this long, complicated thing, and if you want to watch a video on how to derive it, it's kind of interesting. It's not actually as hard as it seems, but it's kind of interesting. It says that A equals R times this 1 plus R over n to the nt, so you should notice that familiar piece from our compound interest formula, but that whole thing is then minus 1. So it's R times that whole quantity, then divided by R over n. And just a quick note that Alex uses M instead of R for the regular monthly payment. So that R right there, you'll see Alex using M. The other books will use other letters, and it's just a matter of paying attention to the definitions. And so we practice using that formula. I'm not going to spend a whole lot of time with this, and I'll show you why. Here's one problem. 3,500 is deposited into account at end of each year for 15 years, 6% annually. So annually means n is 1. So you put that in there, into that whole complicated formula. There's your 0.06 nt, so that's 1 times 15. And then all that quantity is minus 1. And that is 0.06 divided by 1. And so it turns out to be a simplified version is that, and that's what we typed in the calculator to get this number. And so there's that 81,465. So that's how much it would be worth if you started putting that much money into an account every year for 15 years and you were earning 6%. So there's that. Here's another one that's very similar. How much would it be worth? And so I'll let you practice that. And there's the answer. There's what the calculation would look like. So I won't say anything about that. But I will talk about this. And this you're going to like, because these formulas are a little obnoxious to work with. I think it's very important that you try them first, but then go ahead and bust out your calculator. So if you have your TI 83 or 84 with you, you're going to want to get it out, and I'm going to show you this exact problem right here. And it's important that we understand some definitions. So if you look right here, here's the solver that you want to use, and I'll show you on your calculator what this looks like. You go to the apps button right here, you hit apps, option 1, so you just press enter because for finance, and option 1 is the TVM solver. That's what you want. And so there's all kinds of things on here, and I'll talk about them, but I'm actually just going to go to a static version of the calculator screen. If you look, N is a capital N. It's similar to the lowercase n, where the lowercase n, if you notice, is this little 4 right here. That was the number of compoundings. Well, the capital N is 4 times 8. So it's the total number of payments. So it's actually, the capital N in this case is 32. So that's where that comes from. So that's why it says NT, total number of payments. I is the percentage. I is exact, you put in 5.1. The only hard thing there to pay attention to is when we have a percent, we always say we enter it as a decimal. So when we see 5.1, to do an actual calculation in a formula, you type 0.051. But when you're going to use this nifty calculator tool, you actually just type 5.1 like it was a percent. And the clue there is it already has the percent symbol. And then the rest of this, we got to really understand some things. The present value is 0. So in other words, that means you're starting off with no money. The payment is $225. You enter that as a negative value. And that has to do with kind of the way this thing is programmed. And so then you move the cursor to alpha. You move the cursor here and do the alpha enter, and I'll show you that in just a second. The payments per year and the compoundings per year both need to be set to 4. That's because the lowercase n is 4. So that little n and big N show up there. That's important to pay attention to. And then this is what we're trying to calculate. We're trying to find out how much is it going to be worth, the future value. So we already know the answer. That's that 8822.36. So I'll let you see this happen live now. So we go here, big N, we said was 32. Press enter. The percent was 5.1. We press enter. Present value is 0. Payment, I'm going to just delete that. You can type 0 for now or just ignore it. Future value is what I don't know. I'm sorry, payment we do know. Payment was the one that was 225, so we put that in as negative 225. So negative 225. And then, oops, I got off a row. Negative 225. Future value is, you can put anything because that's what we're going to calculate. But payments per year has to be 4. And after you hit enter, it will change compoundings per year to automatically match it unless you want it to be different. So ordinarily these are the same. And so then you go back to the one you're trying to calculate. And if you notice on the screen that I shared, the little dot is right next to future value right here. That tells you that's the thing that you calculated. So I got to go here. Currently it says 0. And the way to calculate it is you press the green alpha, and then notice above enter it says solve. So boom, and now it did that calculation for me. So the future value of that annuity is 8822.36 rounded to the nearest penny. And so there is how you do that calculation without having to use that nasty formula. You're welcome. Let's practice that again. If we go here, I'll show you that one more time on this. This question says, what's the interest from an annuity? Well, the interest would be, you got to figure out how much is in it, and then the interest is just subtract what you had total, so that's the total that you end up with, is that 5 million whatever. You subtract the number of payments. So you put $2,500 end of each month for the next 35 years. So 12 times 35 times 2,500. So that's the total that you put in, is this. And then the total that it's worth is this 5 million. So you subtract those two. That means 4,684,000 and some change is the interest that you earned on that particular investment. But as far as the calculator bit is concerned, we use this annuity formula, the future value of the annuity, and so I could put in all these details rather than this formula, and I'm going to get this 5 million number. So I'm going to show you that practice just for a second one more time. And so NT is 420. That's why I put that out here. 12 times 35. So the total N, the big N, is 420. So that big N up there at the top is 420. The interest is 8%. So 8. Present value is 0. Future value we put 25, or payment we put, negative. I hit the subtract button. Negative 2,500. And then that said it was compounded monthly. So that means payments per year is 12. And compoundings per year, as soon as I hit enter, it changes to 12, and I go up to future value, and it has that other number from the previous problem. But when I hit alpha and solve, I get this $5,734,706.21, and that's exactly what you get if you do this calculation correctly. So hopefully you practice this a few times, get comfortable with the calculator, and you've really got something that you'll like. So one of the, I'll say, tougher questions that you're asked on ALEKS, and this is the last one that we'll do, one of the tougher questions is, how much money do you have to put in the account? So in other words, what's the regular payment? ALEKS calls that M, we call it R, it doesn't really matter. What's the regular amount that you have to put in every month, or I guess in this case it's every year, for 25 years, 7% compounded annually, to obtain a goal of $125,000. So you're trying to get an amount, that's a future value, so that's why the $125,000 goes here. And I'm trying to figure out how much I put in every year in this case. In other words, what's the regular payment? And so I can substitute all the key information in this formula, do all this calculation, and I have to get R by itself, so I have to do some algebra. So that means I clean this up, I can multiply both sides by 0.07 and divide both sides by this 1 minus 0.07, or sorry, 1.07 to the 25th power minus 1. So I divide both sides by all that to get R by itself, and you get this. And so practice that, look at that carefully. Make sure, I encourage you to challenge yourself to do this by hand, but the other way to do it is to put all this information in here, that N is 25, that's the big N. The little n is just 1 because it's compounded annually, 7% interest. 125,000 is the future value, and then you go to the payment and do the calculate thing there. So I'll show you that live so you see what that looks like. So let's see here, get all the information. 25, 7%, and 125,000. So I can remember all that now. So N is 25, 7%. Payment I don't know, so I'm just going to leave that alone. Future value, I want it to grow to 125,000, and it's compounded annually, so I set that to be 1. And then this is what I want to calculate. So I go here and then hit solve. So again, I can delete this or type 0 or type anything, but this number was from the old problem. But while the cursor is here, if I go alpha and solve, then there's my payment. So that means I need to put $1,976.31 in some account that pays whatever that says it does. 7% interest compounded annually, and if I do that, I'll have $125,000 after 25 years. So again, using the calculator, handy. Encourage you to practice doing that and ask questions on Teams, anywhere else if I can help.